I want you to imagine that you are standing on the shore of a frozen sea at night. Far away, beyond the ice and darkness, a lighthouse flashes once, not repeatedly, just once, a single pulse of light. Under ordinary conditions, you would expect that flash to reach you cleanly. Light travels, your eyes receive it. The story is simple. But now imagine the sea is covered in an almost endless moving fog, not thin fog, a thick, luminous wall of frost and vapor, so dense that any narrow beam should scatter, dissolve, and vanish long before it ever reaches the shore. And yet, somehow, impossibly, you still see the flash. That is the feeling astronomers had when the James Webb Space Telescope observed a galaxy called JADES GSZ 13131. This galaxy is not nearby. It is not even merely distant. It is seen as it existed only about 330 million years after the Big Bang, at a redshift of about 13. That puts it deep inside one of the most mysterious chapters in cosmic history, a time when the universe was still emerging from its long primordial darkness. And Webb did not simply detect the galaxy, it detected a signal that should have been extraordinarily difficult to see, a strong signature known as Lyman-alpha emission. I need to tell you immediately what this does not mean. It does not mean Webb has broken physics. It does not mean astronomers have discovered a supernatural message. It does not mean the early universe ignored its own rules. What it means is subtler and therefore much more interesting. The early universe may have been changing faster, more unevenly, or more violently than our simplest pictures allowed, because that signal, that particular kind of light, should have been swallowed by the cosmic fog, and it was not. And that is the door. And tonight, I want to show you why one thin spectral line from a tiny galaxy may be forcing us to rethink how the first transparent regions of the cosmos were born. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to follow the places where observation presses against the edge of theory, you are in the exact right place. Now, I want you to imagine an old room with all the windows covered. No sunlight enters, no stars are visible. The air is filled with smoke. You stand in the center holding a lamp, and when you switch it on, the light does not travel far. It scatters immediately. The room glows dimly, but no clean beam crosses the space. Hold on to that image, because that is roughly what the young universe was like after the first atoms formed. At the beginning, the universe was hot, dense, and ionized. Electrons moved freely, light was constantly scattered. Then, as expansion continued, the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event, often called recombination, made the universe transparent enough for the cosmic microwave background to begin its long journey toward us. But transparency at one wavelength does not mean transparency in every sense. For a long stretch of cosmic history, the universe contained enormous quantities of neutral hydrogen. Neutral hydrogen is not just empty scenery, it matters. It interacts strongly with particular wavelengths of light. One of the most important is Lyman-alpha, a specific spectral signature produced by hydrogen when an electron transitions between energy levels. That line has enormous value in astronomy. It can reveal star formation, hot chunk systems, and energetic processes in galaxies. But it also has a problem. Neutral hydrogen loves to scatter it. That is why Lyman alpha becomes such a powerful test of the early universe. If the space between a distant galaxy and us is filled with neutral hydrogen, then Lyman alpha photons do not travel in a straight, carefree way. They're deflected, absorbed, re-emitted, and effectively erased from the clean signal we would hope to observe. The early universe, in that sense, was fogged. This is tied to one of the grand transitions in cosmic history, reionization. I want you to imagine dawn over a vast frozen field. At first, the field is dark. Then, small fires begin appearing in the distance. Each fire melts the frost immediately around it, creating a clear patch in the ice. As more fires ignite, the melted circles grow. Eventually, the circles touch. The frost retreats, the field becomes opaque. That is one way to picture reionization. The first stars, galaxies, and perhaps early black holes began pouring energetic radiation into the universe. That radiation ionized the surrounding neutral hydrogen, carving out transparent bubbles in the fog. Over time, these bubbles grew and merged until much of the cosmic haze was lifted. The key point is timing. The broad reionization process was not complete until roughly a billion years after the Big Bang. But JWST says 13.1 is seen only 330 million years after the Big Bang. That is early, shockingly early, far too early by simple expectation for us to see a clear, strong Lyman-alpha signal from such a distant galaxy. And yet Webb saw it. Here is the hard truth. The signal should not have been easy to get through. And so astronomers were forced to ask a question that sounds almost simple, but reaches very deep. What cleared the fog? To understand why the question is so serious, I want you to imagine a train station buried in snow. You are waiting for a whistle from far down the tracks. If the storm is thick enough, no whistle should reach you cleanly. Sound is swallowed, broken, smeared into the weather. Then suddenly one sharp note cuts through the blizzard. Your first reaction is not that sound has stopped obeying physics. Your first reaction is that something about the path between you and the train is not what you thought. Perhaps the wind changed, perhaps a corridor opened, perhaps the train is far louder than expected, perhaps the storm is patchier than it looks from where you stand. Astronomers face the same logic. Lyman-alpha from such an early galaxy suggests one of several possibilities. Maybe JWST's Z13.1 sits inside an unusually large bubble of ionized hydrogen. Maybe the galaxy is producing an unexpectedly intense amount of ionizing radiation. Maybe there is a powerful source hidden inside it, perhaps a growing black hole or active nucleus. Maybe surrounding galaxies contributed, helping clear the local environment. Maybe the motion of gas inside the galaxy shifted the Lyman-alpha photons enough that they escaped scattering more easily, or perhaps reionization itself was more patchy, more advanced in some regions, and less uniform than simplified models assumed. Each possibility tells a different story about cosmic dawn, and none has yet won the argument completely. This is where the beauty of spectroscopy enters the scene. I want you to imagine a sealed envelope. From the outside, the paper tells you almost nothing, but if you hold it up to a special light, hidden writing appears in the fibers. A telescope image can tell you that an object exists. A spectrum tells you what it is doing. Webb used its near-infrared spectrograph, NIR spec, to spread the light from JADES GSS 13.1 into its component wavelengths. In that spectrum, astronomers found the Lyman-alpha feature and confirmed the galaxy's extraordinary redshift. The signal was not a vague impression, it was a measurable line. And the line matters because it behaves like a confession. It tells us not merely that there's a galaxy there, but that light associated with hydrogen escaped from that system under conditions where many of us would have expected it to be suppressed. The universe is not silent. It is whispering where the fog first broke. Hold on to that phrase, because in a deeper sense, this is not just a story about one galaxy. It is a story about how the universe became see-through. For a long time, astronomy treated reionization as a kind of gradual large-scale transition. The broad picture remains correct, but broad pictures can hide texture. A wall may look smooth from far away and cracked up close. Webb is giving us the close-up. JADES GSS 13.1 suggests that by 330 million years after the Big Bang, at least some regions of the cosmos may already have hosted surprisingly transparent environments. That does not mean the whole universe was clear. It means the first windows may have opened earlier or more dramatically than expected. Now I want you to imagine a city at night during a blackout. Nearly every building is dark. Then one tower switches on every floor at once. From miles away, that tower becomes visible long before the rest of the city recovers. A galaxy like JADES ZZ13, the first, who may be doing something similar. Perhaps it is not typical. Perhaps it is exceptionally effective at producing or leaking ionizing radiation. Young, massive stars can flood a galaxy with ultraviolet light. If enough of that radiation escapes into surrounding space, it can ionize the nearby hydrogen and create a transparent bubble. In that case, the Lyman-alpha signal would not mean that reionization everywhere had advanced dramatically. It would mean this galaxy was unusually efficient at clearing its neighborhood. That explanation is appealing, but it also has a cost. To carve out a bubble large enough this early, the galaxy must be doing a great deal of work, and astronomers have to ask whether the visible stellar population alone is sufficient to explain it. And this brings us directly to another possibility. What if the galaxy contains an active black hole? I want you to imagine a furnace inside a house. From outside, you notice the windows going brighter than expected. The house itself looks small, but the heat pouring from it feels out of proportion. A growing black hole can do something like that. As material falls inward, it heats up tremendously and releases huge amounts of energy. If an active nucleus is present, it could provide additional ionizing radiation, helping carve out the clear region required for Lyman alpha to escape. This is not a confirmed explanation for JWST 13.1, but it is one of the scenarios astronomers have to consider because the early universe may have hosted energetic black holes sooner than our older intuition preferred. Notice what is happening here. One spectral line is suddenly connected to star formation, galaxy evolution, resonization, and early black hole growth. A narrow signal opens a very wide door, and that is often how cosmology works. A tiny deviation in a graph can force a major revision in the story. Now I want you to imagine a locked room with light leaking from underneath the door. You cannot see the lamp inside. You do not know who switched it on. But the line of brightness under the threshold proves something important. The room is not dark anymore. Lyman alpha in JWST 13.1 is like that. It does not tell us every detail of what happened inside the galaxy or the surrounding intergalactic medium, but it proves that somewhere, somehow, enough ionization occurred for this signal to survive. That alone is extraordinary because for years, one of the central challenges in observing the first few 100 million years of cosmic history was exactly this problem. The universe should hide much of what we most want to see. The first galaxies did not form in a modern transparent cosmos. They formed in a partially opaque one. Their most useful lines were expected to be difficult, perhaps impossible, to detect cleanly at extreme redshift. Webb has been dismantling that pessimism piece by piece, and JADES GSS 13, the 1st of May, be one of the most dramatic examples. This is where the universe, as I have learned time and time again, reveals its deeply humbling sense of humor. We built Webb to look deep into time, expecting that distance alone would be the great challenge. Instead, the universe has reminded us that time comes with atmosphere, not an atmosphere like Earth's, but a cosmic environment that can hide, distort, and erase. Webb is not just seeing farther, it is catching the early universe in the act of becoming transparent. And here's the hard truth. No one yet has a single universally accepted explanation for why this signal appears so clearly, so early. That does not mean no one has ideas. It means the ideas are still competing. And one explanation is that reionization is highly patchy. Certain regions may have reionized much earlier than the average. If JADES GSC 13.1 lives in one such region, the problem softens. Another possibility is that this galaxy belongs to a group nearby. Companions could collectively produce enough ionizing radiation to open a larger transparent bubble than one small galaxy could manage alone. Another possibility is the internal motion of gas. If the Lyman alpha photons are shifted slightly in wavelength as they scatter through outflowing material, they may avoid the worst interaction with surrounding neutral hydrogen. Still another is that there is an active nucleus or unusual stellar population producing an exceptionally hard radiation field. Each of these ideas preserves physics, but each points to a different early universe, a patchy universe, a clustered universe, a violently outflowing universe, a black hole assisted universe. And that is why the signal matters so much. It is not merely unexplained. It is discriminating among futures for theory. Now, I want you to look around the room you are sitting in right now. Light behaves so obediently in ordinary human life that we barely notice it. Lamps turn on, screens glow, windows brighten. We assume visibility, but the universe earned that visibility historically. There was a time when space itself was not an easy medium for certain information to cross. The fact that the cosmos is broadly transparent now can lull us into forgetting that transparency had to be created. The first galaxies were working inside a problem we no longer experience directly. They were helping transform the universe from a place where light was trapped or scattered into one where light could travel immense distances cleanly. You and I live downstream from that victory, and Webb is watching some of its first successful breakthroughs. Think about the sheer weight of that. A few photons left a small galaxy when the universe was still in its infancy, and those photons traveled for over 13 billion years. They crossed expanding space. They survived intervening cosmic history. They entered a telescope orbiting far from Earth. They were sorted by wavelength and translated into a spectrum. And from one subtle line in that spectrum, human beings inferred that the fog of the young universe had already begun to lift, at least somewhere far earlier than we expected to see so clearly. That is almost difficult to believe. Not the galaxy, the chain of reasoning. This is why astronomy is so often an exercise in respectful audacity. We do not touch the object. We do not visit the galaxy. We do not sample its gas directly. We infer. And when the inferences converge, reality becomes visible through mathematics. Now I want you to imagine a map of an unexplored continent. At first, the coastline is approximate, the interior is blank. Then one expedition finds a river, another finds a mountain range, a third discovers that the desert everyone expected is actually broken by forests. JWST 13.1 is that kind of discovery. It does not redraw the entire map by itself, but it makes one old blank region more complicated. Cosmic dawn is not a smooth, uniform wash of gradual change. It may be a terrain of early clearings, intense local events, and asymmetrical transitions. That matters for everything that came later. Reionization is not a decorative footnote in cosmology. It shapes how the first galaxies grow, how radiation escapes, how gas behaves, and how structure develops across the universe. If the earliest transparent bubbles formed differently than expected, then our models of early galaxy formation have to respond. And the question is no longer simply when did the fog clear on average? The question becomes who cleared it, how, and where first. That shift from average to mechanism is where science becomes alive. This is the moment everything changes because Webb is not giving us only isolated, pretty images. It is creating a population study of the early universe. As more extreme redshift galaxies are observed spectroscopically, astronomers can compare them. How common is unexpectedly strong Lyman-alpha? Do these galaxies tend to cluster? Do they show signs of unusual radiation fields? Are active nuclei involved? Are transparent bubbles larger than simulations predicted? One detection is a challenge. Several detections become a pattern. A pattern becomes theory pressure. And theory pressure is healthy. The universe is under no obligation to match the first clean story we write about it. And sometimes it does. Often it almost does. And almost is where the deepest discoveries live. Suppose future observations show that JADES GS says 13.1 is rare. Then we may conclude that it occupies a special environment or contains a special engine. Suppose instead that many very early galaxies show unexpectedly transmissive conditions, then reionization itself may need to be modeled as more advanced, more locally violent, or more topologically complex than our earlier treatments assumed. Suppose early black holes are commonly involved. Then the story of cosmic dawn becomes partly a story about black hole assisted transparency. Suppose stellar populations are enough after all, but only if escape fractions are much higher than assumed. Then the first galaxies were better at changing their universe than we imagined. Every answer reaches beyond one signal. This is what makes the phrase no one can explain useful only if we use it responsibly. In popular language, unexplained can sound like hopelessly mysterious. In science, unexplained often means something more exciting. It means the measurement has arrived before consensus. That is not failure, and that is the frontier. The proper scientific response to such a signal is not panic, and it is multiplication, more data, more spectra, more galaxies, more simulations, more arguments, more patience, because explanation in science is not a slogan. It is a structure built slowly until independent lines of evidence meet. Now I want you to imagine a pocket watch once more. The face seems simple enough: hours, minutes, seconds, a clean visible order. But if one hand begins moving strangely, you open the back and discover a hidden gear train whose interactions are far more complicated than the face suggested. JWST 13.1 is a strange motion of the cosmic watch hand. The visible story of reionization seems straightforward at large scale. Then this galaxy appeared and told us that one of the hidden gears was turning faster, earlier, or more unevenly than we thought. The universe is still keeping time, but the mechanism is richer. And this brings us to a deeper philosophical point. We often speak as if the early universe were primitive, and in one sense, it contained fewer heavy elements, fewer generations of stars, less evolved structure. But primitive does not mean simple. A young rainforest may contain fewer ancient trees, yet be full of fierce competition, rapid growth, and unstable conditions. The early universe may have been similarly intense, compact, energetic, patchy, quick to transform under the pressure of the first luminous sources. In that environment, a signal like Lyman-alpha is not merely a line in a spectrum, it is evidence of local history. Something happened there, a bubble opened, a corridor cleared, an engine burned hot, and the fog retreated. And for one moment in cosmic dawn, the universe allowed a message through. I find that almost unbearably beautiful because it means light was already negotiating with darkness at the beginning. The transparent cosmos we live in now was not simply given, it was won region by the first objects that learned how to flood their surroundings with energy. A small galaxy at redshift 13 is not just an isolated island of stars. It may be one of the first successful architects of visibility. Now it is our turn. Newton taught us how gravity shapes motion. Einstein taught us how space-time shapes gravity. Quantum theory taught us that light and matter behave in ways human intuition never requested. Modern cosmology taught us that the universe has a history. Webb is now teaching us that this history contains texture on scales we are only beginning to resolve. The fog did not lift everywhere at once. The dawn did not arrive as a neat switch. It may have come as scattered victories, tiny clearings in a giant darkness. And if that is true, then the first galaxies were not just early residents of the universe. They were active participants in making the universe observable. Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless dedication to distinguishing what the data says from what the headline suggests. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel there, you help make these long-form lectures possible. But before we end, return with me to the images we carried through this journey. The frozen sea taught us why the signal should have been lost. The smoke-filled room taught us how neutral hydrogen scatters light. The fires on the frozen field taught us how regionization opens transparent bubbles. The train whistle in the blizzard taught us why one surviving signal changes our assumptions about the path it traveled. The locked room with light under the door taught us how indirect evidence can prove that a transformation has already occurred. And the pocket watch reminded us that cosmic history has hidden gears. James Webb did not detect a supernatural message, it detected something more powerful, a signal the early universe should have made extraordinarily difficult to see. Lyman-alpha emission from a galaxy only 330 million years after the Big Bang, a flash through the fog, a line in a spectrum that says at least one region of the cosmos became clear far earlier or far more intensely than our simplest expectations allowed. The door is open now. On one side is the old picture, where the fog lifts slowly and uniformly enough that a signal like this feels premature. On the other side is a stranger, sharper picture, where early galaxies carve out clearings in the darkness, perhaps with help from clustered neighbors or hidden black holes, and cosmic dawn becomes a landscape of uneven illumination. Webb has not finished the story. It has given us the line under the door, and the question that remains is not whether the early universe was changing, it was